Hi, everybody. This is going to be our lecture looking at climate changes over a really long time period. So continuing on with evaluating things through the Phanerozoic. But actually now we're going to be looking at, since the polar position hypothesis doesn't work to explain all of those switches from ice house to hot house periods or hot house to ice house, we need to think about what might be the other part of that. And so to do that, we're going to go back and take a look at the components of the climate system again. So that's atmosphere, veg, ocean, ice, and land surface, and look into what happens with respect to carbon during that as that climate varies from those different pieces. In particular, we're going to look at chemical weathering and carbon in the atmosphere, and then look at patterns of climate and carbon in the atmosphere through the Phanerozoic. So again, most of this stuff is covered in some extent in chapter 14, but not to the detail that we go to in this lecture. So again, if you have any questions, just post those to the discussion board and I'll do my best to answer those as they come up. And again, just a reminder that like all those dinosaurs that were part of the Cretaceous, they're now oil. Like that's where oil and natural gas come from, right? Is all that vegetation that used to be there is not there anymore. So that's how old Land Before Time is. So components of the climate system. So we have our atmosphere, ice, ocean, land surface, and vegetation. And then we also have our external forcing mechanisms. And so we're still talking about plate tectonics here in the scale that we're looking at. We're looking at over hundreds of millions of years, what's happening here. And this will be the end of looking at things over that really large time scale. And so as changes in plate tectonics change vegetation, change atmosphere, change ice and ocean and land surface, we start to see interactions between each of these components of the climate system. So one of the questions I want us to talk about now is, where does that carbon go? And in order to do that, I want to just take a quick look at the different types of carbon reservoirs that we have. So our different types of carbon reservoirs, we have vegetation, which again, it shouldn't be a surprise, vegetation is part of the climate system. So we got veg, we've got soils, we've got sediments and rocks, we got deep ocean, upper mixed ocean layer, but upper 100 meters, as well as the atmosphere and what it was like in the atmosphere, before the Industrial Revolution. So one of the things I want us to sort of focus in on now are these numbers that we see here. So we'll go back, find my pen. So the numbers that we see in our diagram here. So soils, 1,560, vegetation is 610, atmosphere is 600. So 600 what? So what we're looking at here is the carbon reservoir in gigatons. So we've got 600 gigatons of carbon can be stored in the atmosphere. 1,000 gigatons of carbon can be stored in the upper part of the ocean. 38,000 gigatons can be stored in the deep ocean. Veg is 610 gigatons, soils 1,560 gigatons. So when we think about the components of the climate system, so vegetation can't really hold that much carbon. Atmosphere isn't storing a ton of carbon. Our ocean has a lot of carbon, so almost when you add up the upper and the deep ocean together, we're at 39,000 gigatons. And soils and sediments and rocks, or land surface, we're over 66 million gigatons. So soils is certainly more stored in there than there is in veg or in atmosphere, but it's nothing compared to the rest of the land surface in terms of sediments and rocks. So all those fossils, all of that oil, natural gas, coal, all of that carbon is stored in sediments and rocks. There's a lot of it. So you can imagine if we take that carbon that's stored in the giant reservoir of sediments and rocks and refine it, put it into our vehicle, it goes out into the atmosphere. There's not a ton of room in the atmosphere for all of the carbon that we could take out of sediments and rocks. So that's going to have an impact on our climate system if we start changing where each of these pieces go. So the other thing about that, so the couple things. So one, I want you to get out of this picture the size or the scale of each reservoir. So sediments and rocks, massive, or so land surface is the largest one. Oceans is another big one. Veg and atmosphere, has some carbon store in it. And then there's nothing on here about ice, because ice cannot store carbon. So that's why there's a 0 beside ice for the size of the reservoir. Now go to the lower part of this diagram, so down on the bottom right of our screen here. I want you to see what each of these arrows mean and the numbers associated with them. So now we're looking at the rates of carbon exchanged in gigatons per year. So the rate of exchange between vegetation and the atmosphere, so just looking at like these two arrows up here, the rate of exchange between atmosphere and ocean is like 100 going from the atmosphere into vegetation and 50 gigatons per year going from veg into the atmosphere. So that's quite a bit. When you look at the exchange between deep ocean and sediments and rocks, it's 0.2 gigatons. And sediments and rocks back into the atmosphere is 0.2 gigatons. So the amount of time it would take to get you 1,000 gigatons from the ocean into the sediments and rocks would take so much time compared to the relative amount of exchange that happens in vegetation and ocean to the relative reservoir size. So there's an inverse relationship between the size of the reservoir and the rate it exchanges carbon. So a huge reservoir, like sediments and rocks, has a very, very slow carbon exchange. Whereas small reservoirs, like the atmosphere and the ocean, the atmosphere and vegetation, have relatively fast exchange rates. And the upper ocean as well has a relatively fast exchange rate with respect to the atmosphere. So keep that in mind. So although we have tons of room for carbon in sediments and rocks, we have no way to get it there. Even exchanges between the upper part of the ocean and the deep ocean is relatively faster than what we have going into sediments and rocks. And that's going to be a problem. So if we're moving carbon around within the climate system, where it ends up, because if carbon is in the form of carbon dioxide in the atmosphere, it's going to end up serving as a greenhouse gas. So one of the pieces that this comes down to is understanding how that chemical weathering, so the removal of carbon from the atmosphere through chemical weathering, can maybe work as Earth's thermostat. I just need to move this other little piece here. Here we go. So what we're going to look at now is the average rate of weathering depends on Earth's climate is the other part of that. So just taking a look at the top right diagram here. So you have some initial condition and some initial change leads to slightly warmer temperatures, warmer climate. That means warmer temperatures, more precipitation, more vegetation. All three of those factors contribute to increased chemical weathering. And increased chemical weathering, so taking carbon out of the atmosphere, results in removing that CO2 from the atmosphere. If you remove CO2 from the atmosphere, you end up with the reduction of that initial warming. The dog doesn't want to stay here for this lecture anymore. I don't know what that means. Just going to keep going. So that's an example of a negative feedback, right? So our initial condition, so whatever that initial change was, ends up being reduced. That's a negative feedback. Even if it means warmer temperatures, it means it's still a negative feedback because we're reducing that initial condition. And so weathering can end up altering the state of Earth's climate depending on the rate that CO2 is removed from the atmosphere. So if we remove CO2 quickly from the atmosphere, we end up with cooling. If we add CO2 to the atmosphere, we end up with warming, can potentially happen. So again, an example of a negative feedback. And then again, those factors that contributed to chemical weathering are things like warmer temperature increases the rates of chemical weathering. Cooler temperatures, we have less chemical weathering. More precipitation, more chemical weathering. Less precipitation, less chemical weathering. And vegetation depends a little bit. So plants and plant life increases when temperatures are warm. More plant life usually means the more organic acids and whatnot, and that can lead to additional chemical weathering from soils. When we look at changes in climate, so warm, cool, looking through the last 540-ish million years, we can see that things were cooler and warmer. And again, this graph here at the top of the graph up here, this means it was warmer. At the bottom of the graph, this means it was cooler. And we see that there's episodes throughout the Phanerozoic where we had glacial periods, so significant significant amount of ice on the Earth's surface at a given time. So when we look at that through time, we've got some switches back and forth, and we're using a proxy for temperature, looking at the amount of delta O18, which is an oxygen isotope that came from ocean sediments. And so this is giving us an idea, is it warmer or colder because of that, looking through time. So we can see through the last 500 plus million years, we've had episodes of cooler and episodes of warmer temperatures. Those are those hothouse, icehouse eras. When we look at that, think about that, and now look at the amount of carbon dioxide that was in the atmosphere, way back at the beginning of the Cambrian, all of our models, and again, there's some uncertainty here, that's what this big yellow sort of highlight is around these lines. All of these models suggest that the amount of CO2 in the atmosphere was much larger than it is right now. So here we are right now with the amount of CO2 in our atmosphere, kind of sitting at around almost just over 400 parts per million. But just 200 million years ago, some estimates say that it was a little bit higher than it is now, to being like 2,000 parts per million. And again, I really want you to recognize that there's quite a bit of uncertainty and quite a big difference between each of these estimates for the amount of carbon in the atmosphere. But when we go back through time, we see that the amount of carbon dioxide in the atmosphere has varied a lot compared to where we are today. And so this is helping us to understand that in addition to those things like where land masses were, so those tectonic forcing, we have something else going on within the climate system, the amount of carbon dioxide in the atmosphere that's driving these shifts or switches in climate change through time. So to summarize this lecture, we were looking at carbon reservoirs and how they're linked to components of the climate system. We looked at the exchange rates between those reservoirs as well as the relative size of each of those reservoirs. Then we spent some time looking at the feedbacks and chemical weathering's impact on carbon in the atmosphere. So if you're increasing chemical weathering, you're removing it from the you're removing CO2 from the atmosphere, as well as looking at the relative temperatures, again, those hothouse, icehouse eras in the Phanerozoic, and that we did that using the oxygen isotopes and from the ocean, and then estimating the amount of carbon in the atmosphere through the Phanerozoic. So what we saw was, in addition to having, you know, icehouse, hothouse, all those hothouses line up to having higher amounts of CO2 in the atmosphere than we have today. All right, guys, this is the end of our really long timescales of climate change. And the next stuff is going to happen in our next week of lectures, and when we're looking at sort of medium to short-term changes in Earth's climate. So everything that we've done so far will be on our next quiz, and I will get that posted when I get these guys posted. I can't figure out how to finish my lecture, so it's just this sort of weird me talking. There we go. There's the menu. All right, guys. Hope everything's going well, and I hope that made sense. If there's any questions, please let me know. I better go walk my dog now. Take care.